Assalamualaikum warahmatullahi wabarakatuh. Pada kesempatan kali ini, kita akan membahas mengenai hukum ampere.
Okay, I'd like to tell you about the magnetic field at the center of a solenoid. So a solenoid is a tube that has just a bunch of wire wrapped around it and then a current flowing through it. And when you do put a current through there, there's going to be a magnetic field, a very strong magnetic field at the center of the solenoid. And so we'd like to derive some equation that will tell us just how strong that field will be. And as you might guess, it's going to probably depend on how much current we put through there and just how many wires we have there. So let's take a look at the magnetic field at the center of the solenoid. Now to do this, what I'm going to do is, can you imagine me taking this and just slicing it in half like that and opening it up and showing you a cross section of the wire? Okay, now if we did that, if we looked at it from that perspective, then it's kind of important that you understand this picture. So this picture is like if current's flowing into this wire, I'll put an X there, then it's going to loop around. It's going to do like a spiral staircase thing like this. So it's going to go shoomp, shoomp, da-da-doom, 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 and come out this end. So for every X, there's a dot. X, there's a dot. X, there's a dot. X, there's a dot. This is the cross section of the wire. So like this is just a, like if I sawed the wire, that would just be a small cross section of the wire. Now in reality, they don't put space between these. They're tightly wound. In fact, the equation we're doing is assuming that it's a tightly wound solenoid. But I'm going to not do that for right now because I want to make a couple points. So dot, 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 dot. Okay, so if you get what I'm saying, there's a wire that comes through here, and then it comes around like this. So it's this wire's closer to us maybe, and then it loops this way, and then this way. I'm just drawing the spirals. It's kind of important you get this picture, or you're not going to get this derivation. So it just spirals like that, you know. So it goes shoomp, shoomp, shoomp. We're kind of looking at a cross section of the solenoid. Okay, I'm hoping at this point you're going, I get it, go on. Okay, because now I'm ready to go on. Okay, so if we look then at the field, say due to this guy right here, just that wire right there, if I put my thumb in the direction of the current, oops, the current's into the page, so it's going to be going around like this. Let me draw it in red. It's going around like this, just due to that part of the wire. Whereas the one here, that's going like this. And so you see how the field from this wire right there is that way, and the field from this wire right there is this way. Those cancel out. So the fields cancel out here. And what happens is that these meld together with these. Let's just do this on this side for a second. So it's going to... Magnetic field lines are always closed loops. Yeah, same thing's happening over here. These are canceling each other out. And so what we have here is these are going to meld together and give you this field like this. It's going to go out. Oops. Kind of messing this up a little bit, but the point is that these lines, these field lines get pinched together in here, and you get this strong magnetic field. Again, don't think that these lines are just ending somewhere. They actually keep going, and they're going to circle around. Okay? So we get a really strong magnetic field inside there. And the rest of this video is to show you how you actually calculate the field right at the center of that. The field right at the center of that solenoid. Okay, so let's take a look. Same picture. Okay, and what I'm going to do is we got this field going around in there. Remind you that these are some X's, and these are dots. So you got this field going around, and I'm going to draw an Amperian loop in maybe green. I'm going to make this Amperian loop go like this. It's going to go like that, like that, and it's going to go all the way out to infinity. So let me break it like that. Those aren't resistors. That's just to remind you that this is going out to infinity. So that's my Amperian loop, and I'm going to make this point A, B, C, and D. Those are the 4 points on the Amperian loop. Now remember, there's a field then that's going like this. I'll just show you a couple field lines. It's going like this, and it loops around out here and comes back down this way. So that's the field. This is the magnetic field. And let's have the DLs for the Amperian loop go like this. Those are just a bunch of DLs that I'm drawing. They come by this way too. They go around the whole thing. Okay, so let me go ahead then and apply Ampere's law. But I'm going to say that, would you agree there's some current going through the Amperian loop, maybe 2 of these? So whatever the current is, if this is, say, I, I'll make it a lowercase I. If that's I, then the solenoid doesn't, or the Amperian loop doesn't know that those are the same wire. It's going to just think that those are 2 separate wires. So it's going to see 2I through there. So I'm going to do, on the one side of Ampere's law, I'm going to say that it's mu naught, this is Ampere's law, but I'm going to say it's mu naught times 2I, because it's going to see it as 2 times the current. Okay, now I have to break this into 4 different integrals. It's going to be the integral from here from A to B, from B to C, C to D, and D to A. So I'm going to do that. I'm going to break this into the integral from B dot dl. It's no longer a closed loop. I'm going to go from A to B plus B to C plus C to D. No, C to D. I'm running out of space here. Plus, I got to put this one down here, B dot dl from D to A then. Now that's a closed loop. Okay? So, I got to find the integral for all those. Now, it turns out that the integral for this one, for this path, from B to C, that because of the dot product, you see how DLs are always perpendicular to the B field? And so that's going to go to 0. And same with the one from D to A. Because the B is perpendicular, the B is this way and the DL is that way, those are going to disappear. And so, and this one's going to disappear because you're at infinity. So the B is 0 out here. So when you do 0 dot DL, you're going to just get 0. So the only integral that's going to survive is this middle one. So, or the one that's in the side, the solenoid. So from A to B, that's going to survive, but this is going to go away. From C to B is going to go away because of the dot product. And so is A to D. That's going to disappear because of the dot product, because B is perpendicular to DL. And this one out here from C to D, that's going to disappear because B is 0. So now I'm just left with that. Okay, I'm not going to finish this. I'm going to need one more to finish this. So I'm going to say goodbye and finish it on the next one. Okay, bye. All right, here's the magnetic field due to a toroid. So let me first tell you about a toroid. Toroid is like a donut with a bunch of wire wrapped around it. It's almost like a solenoid that you've taken and you bend it in on itself so it wraps around itself. So, and then you put current through it. And so you get these magnetic fields inside the toroid. And so let's say that the current comes in like this, and then it circles around and it does all this. It's going, I won't draw it in every one of these, but I'm thinking it's going like this. And then it comes out this way. So there's this current that's flowing in there. It flows around, shoom, 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 like spirals around. Okay, so that's a toroid. Spelt again like this. Now, if we would like to know we'd like to know what the magnetic field is when you're a distance r away from the center, and so whether we want to know what the field is here, in here, and then finally out here. Okay, so I'm going to draw this. I'm going to take this and I'm going to slice it like a bagel. Can you imagine a bagel sitting here? And I take a knife and I slice it. And I cut it in two halves to put some cream cheese on it or something like that. Well, when you do that, you cut through all those wires. And so now we're looking at the cross-section of the wires. So let's say the current comes in here, and the first thing it does is it comes in and makes a dot, then it circles around and goes and makes an X. And then it makes a dot, and then it makes an X. And then it makes a dot, and then it makes an X. And then it makes a dot, and then it makes an X. It's going shoom, 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 like that. Okay, and that goes all the way around. So there's nothing but dots here where the current is coming out at us. And then on these, there's nothing but X's. Okay, so it turns out then that the magnetic field in here is what you're going to get when these go around like this, is that when the current goes around, is you're going to have field. See how that's a dot coming out at us? So you put your thumb out at us, and the field is going to go like this. It's going to be kind of like field lines are going to go like that. They're going to point that way. Okay. So if I want to know just how strong that field is going to be in there, I'm going to draw an Amperian loop. We'll make it green. So the Amperian loop is going to start here, let's say. Just draw a dotted line around here. Now the field is going this way, then it's going this way, then it's going this way, then it's going this way. And I'm going to apply Ampere's law now. So mu naught times I is equal to the closed loop integral of B dot dl. Now that's the I through the Amperian loop. Now the Amperian loop doesn't know that this is all just one wire. It thinks that there's all these different wires that are going through it. So if the current in here is I, it thinks that there is however many loops there are, that's how much current it thinks, that times I. So if this is 2 amps and 2 amps and 2 amps, this thinks that the Amperian loop is going to, if you asked it, it would say how much current's going through it. 2 amps plus 4 amps plus 2 amps plus 2 amps plus 2 amps, that's all those added up. So I'm going to say that this is equal to mu naught times N times I, where N is the number of coils you have. That's how much current is going through the Amperian loop. Now, you see how the dot product disappears because B and DL is in the same direction? The dot product disappears, so get rid of this guy. Okay, now, why, because of symmetry, why would B be any stronger here than here, than here, than here? It shouldn't be. So I'm going to pull that B out of the integral. And I'm left with summing up all those DLs. When I sum up all those DLs, if I'm out here at distance r, when I sum up all those DLs, it's going to give me B times 2 pi r. So the magnetic field in a toroid, if I bring that stuff on the other side, it's going to be mu naught n I all over 2 pi r. This is the magnetic field due to a toroid. Okay, now it turns out though that the field gets totally contained in there. None of it goes in this section and none goes outside. It's completely contained in there. Let me show you why. I'm going to drop an Amperian loop in here. Okay, in that Amperian loop, how much current is going through there? How much current is going through this Amperian loop? The answer is none. There is no current going through there. Okay. Well, then if the I is none, then the B is going to be none. Okay. This picture's a little messy, but let's just look one more time then. Remember, these are dots here, and these are X's. And to get the magnetic field outside of the toroid, like out here, say right here, I'm going to draw an Amperian loop. That's my Amperian loop. It's circular. I know that's a really bad circle, but it's circular. Out here at distance r. Now, if I asked you how much current's going through that loop, I would again say none. Because we might have a lot of this current, but for every dot we have an X that goes with it. So if this is 2 amps out of the page, this is 2 amps into the page. 2 amps out, 2 amps in. So they always negate one another. So the total current is going to be 0. So that means that your field is going to be 0 out there. Okay, so field is 0 here, no field there, no field here. But in here, in this region, there is field. What's the field in there? The field in there can be easily derived as mu naught Ni over 2 pi r. If you think about that, that's not a tough derivation. If you understand Ampere's law, that's a pretty fast derivation. Okay, thanks. Bye.